Today we are going to talk about concavity and the second derivative. Okay, so we've been talking about the first derivative test. And remember that the first derivative test tells us where a function is increasing and decreasing, and it also gives us the location of the relative extrema, the maxes and mins. Okay, if you're still having trouble with that, then you need to email me and let me know so I can help you. Okay, today we're going to talk about the second derivative test. That helps us to find where a function is concave up or concave down and where it has points of inflection. Okay, there could be one point, there could be multiple points of inflection. Before we get into the second derivative test, you need to remember some key vocabulary words that you would have learned in previous math courses. So concave up means that the graph opens upward like a cup. I like to say concave up like a cup. So this graph is concave up. If you think about it, it would hold water, okay? A cup would hold water. Concave down means that the graph opens downward like a frown. So you could either have concave up like a cup or concave down like a frown. Okay, so this one looks like a frown. This guy's concave down. A point of inflection is the point where a graph changes from either concave up to concave down or from concave down to concave up. We shorten its name to POI for point of inflection. So if you take a look at this graph starts off, it's increasing to a maximum, and then it's decreasing to a minimum, and then it's increasing. But it's concave down, and then it switches to concave up. And that point where it switches from concave down to concave up is called a point of inflection. So that's what we're going to be looking for. We're going to be figuring out the intervals. Let's say, just for nice pretty numbers, let's say this is -2. So then this graph would be concave down from negative infinity to -2, and it would be concave up from -2 to positive infinity. Again, this looks like it's more like -1.2 or something like that. Well, actually, it's my scale here. My scale, oh, it's probably like -0.75. Okay, I just realized that my scale is going by a half. Okay. So let's do a problem. I actually had another problem and I don't think it printed. So I'm going to pause the video and I'm going to find the problem. Okay, crisis averted. I found my first example. So the second derivative test works almost exactly like the first derivative test does. Hang on, my printer's going crazy. Okay, I think it's not going crazy now. Okay, so the second derivative test works very much like the first derivative test, except that we do all the same things, but on the second derivative. So instead of setting the first derivative equal to 0, we set the second derivative equal to 0. Instead of testing numbers on either side of the critical numbers, we test numbers on either side of the points of inflection. So the steps are very similar. We're going to find the second derivative, and remember you find the second derivative by finding the derivative of the derivative. We're going to set the second derivative equal to 0 and solve for x. The x values are called the possible points of inflection. We don't know if they're definitely points of inflection, but there are candidates. We're going to plug test values of x into the second derivative on either side of the possible points of inflection to see if the second derivative is positive or negative. If the second derivative is negative, then f of x is concave down on that interval. If the second derivative is positive, then f of x is concave up on that interval. Okay, so let's do an example here. Given the function f of x equals 2x cubed minus 3x squared minus 36x plus 5, we're going to perform the first and the second derivative test to find each of the following. And I have a whole laundry list of things that we have to find here. We have to find where f of x is increasing, where it's decreasing, any extrema, where f of x is concave up, where f of x is concave down, and the location of any points of inflection. And I have this area over here designed as my workspace. So what I'm going to do is I'm going to do all the work over here, and then I'm going to come back and answer these questions. So the first 3 things in this list, these come from the first derivative test. So I need to find my first derivative. So f prime of x is equal to 6x squared minus 6x minus 36. Okay, just doing the power rule, and I set it equal to 0. And I happen to notice something that's going to make my life a little bit easier here. All of these numbers are divisible by 6, so I'm going to divide both sides by 6. Anytime you can make the number smaller, you should do that. So that gives me x squared minus x minus 6 is equal to 0. And now I need to factor this quadratic. So this is a nice easy factoring. I put my x's here. I need a negative 3 and a positive 2. So I get x equals positive 3 and negative 2 are my critical numbers. Okay, so something's going on at those values. Now before I do my number line, I am going to find my second derivative. Okay, so my second derivative, remember that's the derivative of the derivative. So it's going to give me 12x minus 6, and I'm going to set that equal to 0. And I can take the 6 over to get 12x is equal to 6, and I can divide by 12 to get 1/2. So x equals 1/2 is a possible point of inflection. I should really put a PPOI in there for possible point of inflection. And now I'm going to create a number line. And when we did the first derivative test, I had you write f prime of x at the front, and then we put our critical numbers there. Put them in order. Don't put positive 3 before negative 2. I had somebody do that once, and it gets a little bit crazy. I'm going to put my second derivative on the bottom. Can you see that? No, that's not a great color. I'm not going to use that one. Let's use red. Okay, so the second derivative is going to go on the bottom half. And my possible point of inflection is 1/2. So that's somewhere between these two numbers. So I'm going to maybe put it right here, 1/2. So here's what we need to do. I need to test a number in this interval, somewhere to the left of negative 2 into the first derivative, a number between negative 2 and 3 into the first derivative, and a number to the right of 3 into the first derivative. That's just review from last week. Then I have to pick a number to the left of 1/2 and plug it into the second derivative, and then a number to the right of 1/2 and plug it into the second derivative. So I have 1, 2, 3, 4, 5 valuations that I have to do. The first 3 are going to be into the first derivative, and the others, hang on, dumb dogs. Okay, so the first 3 are going to go into the first derivative, and the second 2 are going to go into the second derivative. So let me do my first derivative. I need a number to the left of negative 2. Let's say negative 3. And remember, I don't really care what the answer is, I just need to know if it's positive or negative. So I always like to go back to the factored form of the derivative. That's this guy right here. If I put negative 3 in here, that gives me a negative number. And if I put negative 3 in here, negative 3 plus 2 is a negative number, and a negative number times a negative number is a positive number. So I get a plus sign there. So this is a positive number. Let me pick a number between negative 2 and 3. Well, that's the most easy one to pick is 0. So if I put 0 in here, I get negative 3 times positive 2. Well, negative times positive is a negative. So I can put my negative sign in there. And now I need a number to the right of 3. Let's say 4. If I put 4 in here, 4 minus 3 is positive. 4 plus 2 is positive. A positive number times a positive number is a positive answer. So I have my positive signs there. Now I'm going to do the same thing, the same process, but this time I'm picking a number to the left of 1/2 and plugging it into the second derivative. So what number is to the left of 1/2? Well, 0 is, that's an easy one. But this time I'm putting it into the second derivative. So if I put 0 in there, 12 times 0 minus 6, that's a negative number. So I'm going to put a negative sign there. And then I need a number to the right of 1/2. Let's say 1. I'm going to put 1 in there. 12 times 1 minus 6 is a positive number. So I have a plus sign here. So now, what this number line is able to do is it's able to tell me a lot of information about the original function. The original function is increasing, then decreasing, and then increasing. I have a maximum at x equals negative 2, a minimum at x equals 3. The original function is concave down from negative infinity to 1/2, and then it's concave up from 1/2 to infinity because of the plus sign. That makes x equals 1/2 a point of inflection. So just by analyzing this number line, I have answered all of these questions to the left. So where is f of x increasing? Well, f of x is increasing when the first derivative is positive. Well, that happens from negative infinity to negative 2, and it also happens from 3 to infinity. So there's the answer to A. Where is f of x decreasing? Well, that happens when the first derivative is negative. That happens between 2 and 3, so it's the interval from 2 to 3. The location of any relative extrema, well, x equals negative 2 is a maximum, and x equals 3 is a minimum. Where f of x is concave up, now this is where we switch to the second derivative. All this stuff is second derivative stuff. So concave up where the second derivative is positive, that happens 1/2 to infinity. F of x is concave down where the second derivative is negative. That happens from negative infinity to 1/2. And the location of any points of inflection. Well, since we changed from concave down to concave up, that means that x equals 1/2 is a point of inflection. Okay, so I'm going to stop this video, and then we'll make another one for the next example.